calculus. Calculus is defined as the mathematical study of change. It was developed to its final form by Sir Isaac Newton and Gottfried Wilhelm von Leibniz in the 17th century. Calculus can be divided mainly in two, differential and integral.
While integral calculus concerns about the theory and application of integrals, differential calculus focuses on rates of change such as slopes, tangent lines, and velocities.
But in what ways we can use differential calculus? For once, we can use it in engineering.
A lot of engineers use calculus in their daily practice. Some use it for optimization and summation. Others use it in computational programs to simplify engineering design.
In civil engineering, differential calculus is for the derivation of basic fluid mechanical equations and analysis programs. In hydrology, volume is calculated as the area under the curve of a plot of flow versus time, and it is accomplished using calculus.
Structural engineering is used to determine the forces in complex configuration of structural elements, but it is also used in analysis related to seismic design and activity. Other application is that with calculus, engineers calculate the capacity and strength of soil.
Differential equations can be used in electrical engineering. These can be useful for circuit analysis. For example, if we look at an RL circuit that contains a power source, an inductor, and a resistor, the inductance can be defined by the rate of change of magnetic flux per amount of changing current that goes through it. This is known as the Faraday's law of induction, which explains how an electric current produces a magnetic field. We can also get the voltage, which is inductance, by the rate of current change per time. By using these and the Ohm's equation, we can derive an equation for an RL circuit.
In the following equation, E is the supply voltage constant, R is a constant related to total resistance in the circuit, L is the total inductance of the circuit, I is the current at time t, and V over t is the rate of change of the current in the circuit.
By integrating this, we can get an equation to calculate the current, which is and by differentiating this, we can also develop an equation to calculate voltage at time. This is just one example of how calculus can be used in electrical engineering.
Now, in mechanical engineering, differential equations are used for fluid mechanics analysis. For example, we can use the equation called the Bernoulli's equation, which is the mathematical equation or expression of the law of physics relating the driving pressure and the velocity in a moving non-compressible fluid. Here we can see that in the equation, V means velocity of the water flow and P means the driving pressure. It can be used for analyzing the liquid water flow in a large reservoir.
Application for calculus is diffusion, in which we use the law of diffusion, where F is flux, mu is the diffusion coefficient, and U is the state. The differential form of the conservation law for diffusion is. This can be used to calculate heat conduction, meaning the diffusion of thermal energy. Finally, another application is in aerospace engineering. Differential calculus can be used in the analysis of rockets that function in stages, as does gravitational modeling over time and space.
As we can see, differential calculus has countless of applications in engineering.
And engineering is essential in our modern world as we currently need it for everything.
Which means, whether we believe it or not, differential calculus is almost essential for living.
Thank you. We are Valenzuela,
Marisol Zarate,
And Daniela Acosta.